Okay. Thank you very much. So yes, who am I? This is a, can you see? Well, this is a Linux command where you basically get information on your user. So who am I? My name is Tane Haines. I'm the president at CTF here. I'm a first year student studying a degree in engineering honors, majoring in cybersecurity. In my free time, I code, hack, and play CTFs. And my favorite category is reverse engineering, thus this talk. So, reverse engineering. Now, all software is open source if you get good enough at reverse engineering. But on Twitter, it's true. So, what is reverse engineering? Well, to get into this, I need to start with a description on, well, I guess, some of the history of reverse engineering. This right here is a telemark from the 18th century. The time when, I guess it is said that reverse engineering started because of the rise of computers. However, it started way before this. Back when things like wheels, carriages, and even architectural infrastructure like buildings were made, reverse engineering existed. A very good example is when the Roman army was battling Carthage, they did not have a standing name during the First Punic War until they kind of took over a Carthaginian creamery and I guess reverse engineered it to make 300 of their own ships. They ended up destroying Carthage. Yeah, so now we've done that. I want to introduce you to the different fields in reverse engineering. So modern reverse engineering is things like reverse engineering 3D printed goods. It's kind of like what the Romans were doing. We also have hardware reverse engineering, which is specifically electronic components. So like computers or basically any IoT device like the routers up there, TV screen, your phone. And then we have today's focus, software reverse engineering. Often it's reverse engineering code that is not open source, which means that you can't just go online and find the code and read exactly what they wrote. You need to actually reverse the machine readable bytecode, which I will show in a bit. So let's get back to what is reverse engineering. Engineering is making something, and reverse engineering is understanding how this was made. Now, why do people reverse engineer? Well, there are plenty of different people and plenty of different reasons people reverse engineer, but the main ones are people extremely curious about what the program does, and just like bored and wanting to like find out what the thing does. Some countries and companies wanting to uncover the secrets of other countries or companies. Malicious parties trying to, for example, ransom companies or make hacked clients for games, because you need to understand it to actually make that stuff. People who like making mods for games. Academics who kind of want to understand the concepts used so they can further develop their research. White hat hackers doing bug bounties, so basically people helping companies find vulnerabilities in their programs and getting payment for that. And CTF players, and there are many more out there. Are there any questions so far? Okay. So, reading the binary file. I'm going to start by explaining what binary is. Binary is a collection of ones and zeros, or the official definition is a system of representing numbers using two digits, only 0 and 1, instead of 0 to 9. I'll go more in depth into this later as well. So then what is a binary/executable file? There is a difference between the two. Binary file is a file containing any data. So images, videos, audio files, and programs are included as well. An executable is a file that is runnable or actually run by your computer. So these are just programs because they don't have the bytes in them. Sorry, I made a mistake on that. Basically, a binary file is a file that has data in it, and an executable is a file with data in it that can be run. So today's focus is specifically Linux reverse engineering, but just to introduce you briefly to some other types, there's Windows reverse engineering Android apps, which is in Java, Unity games, Mac OS binaries, WebAssembly, which is on the web, Electron, which is JavaScript, which is actually very vulnerable quite often. You can find some crazy stuff there. And Python bytecode and Lua bytecode. I'll be doing talks on some of these throughout the year, maybe, if people are interested enough. So be on the lookout for those. So I still have a few more things to get into before I show you some actual reverse engineering. Compilation vs decompilation. Compilation is when a program, this right here, is turned into machine code. I'm not sure if you can see it, but right here it says hello. That's the data stored in the file. The rest of it, I believe, is part of the program that was turned into something that is readable by your machine, so your computer or whatever is running this. No, that's compilation. We also have decompilation, which is turning this into what the decompiler thinks it used to look like when it was written. It's pseudocode, but often it looks very similar to C. So I want to briefly also get to disassemblers vs decompilers vs debuggers. Today we're going to be focusing on decompilers, but basically disassemblers are do all of you know the assembly language, or know of the assembly language? Yeah? Okay, I'll explain briefly. Basically, it's the closest you can get to the computer without writing the bytes you saw earlier, and it's actually, if we go back up, right here, instructions like sub is what it says here. This is all assembly, and that would be subtracting, SP minus 0x20, which is 32, right? Yeah. So machine code is kind of like a step-by-step thing where you have the raw data right here. It can basically represent assembly one for one, whereas C, it can't really do that because I guess it's a more high-level thing. I'll probably get a bit more into it later in the talk, but for now I'll move on. So disassemblers basically turn the code into that assembly representation, and I guess let you statically analyze the code. Decompilers convert the disassembly into the C code right here, you saw, so that you can actually read it. However, the disadvantages of doing that are mainly that it's easier for the person who created the program to trick the compiler into not showing all of the code, and you won't notice it because that's all you can see, whereas over here you'll see that like some of the bytes haven't been represented, or like there are parts that I guess have been written but aren't displaying on the pseudocode version. Yeah. So finally, debuggers are quite different. in that you're basically looking at the code while it's running. So the other two were before it runs. You're analyzing that bit. But then debuggers, you run the program, and you can see the instructions as the program runs, I guess. One merit to this is being able to, for example, if they store the bytes of a function, because as I showed you earlier, this is what it is to the computer. If they store that into a variable, you can't see that in the decompiler or disassembler. Like, you can't see what that function is doing. So you can quickly go to that location and, I guess, look at the instructions that the computer is running. It's also useful for very quickly understanding parts of the binary that are kind of hard to understand through static analysis, because it just does it for you instead of you having to go through and getting what each step does. Some demerits of debuggers are that you don't get pseudocode. You don't get the decompiled code. You only get assembly. I'm sure, I don't know of any debuggers that do that. Often, and I guess just if you only have the debugger, it can be hard to find where you're trying to go. Whereas if you look at it through decompilers, you can go, oh, that function seems useful, take that address, and then go to that point on the debugger. Yeah. So now, the difference between static analysis and dynamic analysis. So the disassemblers and decompilers are static analysis tools because you're reading the file directly, whereas debuggers are for dynamic analysis because the code is being run. So these are some decompilers and disassemblers. Most modern tools have both of them together. They have both of them embedded. Specifically, Ghidra, IDA, and Binary Ninja, or Binja, which are the most popular ones. And then Radera 2 is only a disassembler. If you know how to use it, it's much quicker, I'd say. Okay, any questions? Nope. Or was there anything you were confused about that you want me to go over again? No? Okay, cool. So I'm going to get a bit into decimal, hexadecimal, binary, and bitwise operations, just so that it's easier to show you through the first challenge. So hexadecimal in one slide. So they can both also be called base 10 for decimal, base 16 for hexadecimal, because decimal goes from 0 to 9, whereas hexadecimal goes from 0 to F. 0 to 9, and then A to F. A good way to show this would be that 10 to the power of 1 is 10 in decimal, and 10 to the power of 2 is 100, whereas in hexadecimal, in hexadecimal as well, 16 to the power of 1 is 0x 10, and 16 to the power of 2 is 0x 1, 0, 0. But then 16 to the power of 1 minus 1 is just 0xf because it goes up to 15 compared to decimal, which goes up to 9. It'll make sense. I think it'll make more sense if you haven't gotten a grasp of it yet, once I explain the binary. But yeah, this you saw earlier. All of this is hexadecimal, or hex, base 16. Okay, binary on one slide. So binary, on the other hand, is base 2. So it only has zeros and ones. So 10 in binary is literally 2 to the power of 1. 100 is 2 to the power of 2 or 4. 1000 is 2 to the power of 3 or 8. Is that making sense? Yeah. Yeah. So it is a bit, yeah. I want to go into two operations, bitwise OR and then bitwise XOR. So in your daily lives, if you say, I'm going to do this or this, it's usually either this or the other thing. However, in bitwise operations, OR is either this or both. So if one of them is true, then the output is true. I'm going to come to decipher this. So an example here is you want to go 1 byte at a time. You have 3 bytes. So the first one, 1 and 0, it becomes 1 because one of them is true at least. 0 and 0 it becomes 0 because neither of them are true. And then 1 and 1, it becomes 1 because both of them are true, or at least one of them is true. And the same with this. The first two, one of them is true. One of them is true. One of them is true. I think that makes sense, but we'll have a questions if you're still confused about it. We also have a bitwise XOR, which is the OR that you're more used to, except it's called exclusive OR. It's one or the either, one or the other, and not both. So, in the same example from before, the last bit, but these are called bits, they're in base 2. The last bit, both of them are true, so you get false or 0. Whereas the first one, it is just 1 that's true, so you do get 1 as the output. Yeah. Any more questions? Okay. Yeah, okay. So this is the part where I explain how you actually read decompiled code. So I'm going to take you through how to actually use Ghidra. We will guide you through even if you don't get all of it here, but just to kind of bring you into it. So if you go to File and then New Project, you can create a new project. We're going to name it Demo. And then to bring the file in, you can either go here and click Import File, or just click I, and then after here, and then you select the file you want to import, or the file you want to decompile, and then it brings it into your project. If you click on the file, make sure to click on where there's actually text, because otherwise it won't open. I always click around here and then it just doesn't open, which is a common problem. Oh. So yeah, something like this will pop up. So just hit, okay. Oh. Another little window right here that is asking if I should analyze it or have Ghidra analyze the code for me. So click yes. Click OK here. Okay. Usually this would be in the background. I moved it, so I think it changed the order. I just want to move that out of the way. So just click OK on that and click Analyze with the default settings here. And it will turn it into readable C. Well, you'll have a readable C code version and a assembly version. Usually, it just finds main for you and starts there. But in this case, we have entry, which is, I guess, the entry point for, usually the entry point for assembly programs. If this happens, look for the function called _libc start main, and then look at the first function in the list. In Ghidra, things with fun and then some like numbers afterwards are functions. So look at the first function. Click on it, click L to rename, and just call it main. And then click on it to go to it. Okay, so what's happening here? Well, we see a list, you probably are familiar, even if you haven't done C, even just Python. That's a array of 40 bytes, which are 40 characters, effectively. Array of 40 characters. I find that quite suspicious because, I mean, the other ones are just integers. So I guess we'll keep an eye on that. And yeah, we have a lot of values being set into local 38 here. So if we go a bit further down the program, we see a for loop. If you've written a for loop before, the variable used for the iterator, or the thing that usually gets increased each time the code in the for loop runs, is called I. So click L, rename the variable to I, so it's more readable. Because otherwise the variable name is just long and it's messy. Earlier, Ethan described to us that you're looking for flags in capture the flag competitions. This won't necessarily be the case in if you're doing real world reverse engineering, but in our case, that's what we're doing. So I think that if the only thing we have here is a array, that's a list of characters, that's probably the flag. So for now, I'm going to rename that to flag. Now, what are these values? So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Tane, can you please zoom it a little?
Oh yeah. And I just full screen it. Hopefully that didn't make it better, did it?
You pop up the ticket panel off. And zoom.
Oh yeah, it's much quicker.
Is that good?
Much quicker, yeah.
Okay. I can zoom in more.
Yeah.
Do you want to have the ticket panel on its own window? Then that'd be pretty easy to see if it's just its own window.
Actually, I guess we don't need that assembly code. Yeah, that's true.
Yeah, much quicker.
Just do that.
Yeah.
Yep. Okay. So yeah. So we had that 0, 1. We had the list objects. So that's number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 0xb. If you remove your x, that's 11. I can't believe that took me a bit. And over here you have the values as x as well. You can actually, I don't know how you would change it in the lists. I forgot, but you can change values that are being assigned to, I guess, variables or arrays into different forms. So I don't know if you can see here, but the one I'm hovering over right now is binary, and then below it is decimal, and then float, and then double, and then octal, and then you have char. So in this case, the char, if we convert it to char, it'd be x, and then if we convert it to decimal, it would be 88. You can do it for each of them, but I'm not going to because it's not strictly necessary. So actually, I should probably have explained that this part of the code right here, what this part of the code is doing. this is not something that I wrote. It's this thing called a canary check. So the program has a value stored somewhere. And you as a user, if you get prompted and you send the program some data, if you send a lot of data because the program isn't checking that properly, you can go over your allocated part. So you can go into the part of the program that basically you're not supposed to, and can kind of like mess with the values directly in the program. This canary is somewhere in the memory, so that when you do that and the values are overwritten, it notices that the values are overwritten and goes no and just shuts down the program. You can actually bypass this if you can leave the canary. So if you know what the canary value is or can reveal it, and literally just once you get to that location, write the same value into the program. And then after you go on, you can just do whatever you want. But yeah, that's not relevant in this program since we're not needing to exploit that. This right here is a print. Basically, think of it as a print statement. I'm basically taunting you. Hello there. Have you tried decompiling the code yet? I recommend using gdime. This will print out if you actually run the program. But I can't actually run it since I'm on my MacBook right now, and you need a Linux or WSL to actually run it. Okay, now the main part of the code, the form. I might actually have one of you try to suggest something. No, like what is this thing there?
Searching through int I, and then your I being whatever flag variable values are, and to the power of 0x2a times it, or to the power of the I value.
Relatively close. Let's actually, I'm going to really quickly go back. I forgot to be more clear on it. So you have or. The way or is represented in programming is usually a /def. Whereas you also have XOR in programming. It's actually represented with an up arrow.
So it's looking for the variable flag, or it's looking for the hexadecimal value. Is that what you're saying in the for loop? Exclusively or the 0x2a?
I'll get to that in a moment.
I think you're assigning, so your array which you renamed it as flags. So you're assigning each element in your flag up to 20 to the source. So you're storing and you're doing like 0, 1, 2, something like that. You're just storing it like 0, 1, 0, 1, 0, 1, something like that, to each of the value in the array. Something like that.
A bit different. I think you're on the right track. So what this is actually doing is, it's for each value in the flag, it's zeroing it by 0x2a. Actually, in this case, it might be good to convert this into binary.
Yeah.
So let's just take the last value here as well and convert that to binary. So what it's doing is it's zeroing each of the values in here. For example, for this one, the first byte is 0, 0. So that returns 0. The next one is 0, 1. So it would return 1. The next byte is 1, and then over here it's 0. So that would also return 1, and so on. So basically, it's XORing each value within the flag array, or XORing. Does that make sense? Yeah. Does that make sense? Okay. Okay. Yeah. So now that we understand the program, how can we kind of like bring our understanding to recover the values that the program is actually getting? So we basically reconstruct the code. However, well, you can do it in C, but I'm going to be doing it in Python. I actually set up a little demo here. Can you see that? No? Yeah. Wait, how do I? Is it really? Oh, yeah. Wait, you can actually just.
So you
Yeah,
have
that's like-
Yeah.
Nope, I'm just using Visual Studio Code for now.
Use the one little more, please.
Yep. I'll be moving from the terminal to Visual Studio Code. Open. And
you do the same, yeah.
oh, it doesn't have Route either. Probably use Route. I'm always fully thinking that. Okay, cool, thank you. So, yes. So this is the list from earlier. That was assigned the values. I may as well show that. So, if you look back at this, 0x7c, which is hexadecimal, 0x5f, and then we go back to the program, which is 0x7c and 0x5f. So I just put the values in there so that you don't need to see me kind of moving each value from the array into the Python program. And then you want to, I guess, define a string, a variable for a string called flag, and then recreate the program. It was a pretty basic program which just XORed each of the values in the array it was 2a, 0x2a. So so you create a for loop in Python, which iterates over it, and for each value you add its character representation of after it's been XORed with 0x2a. And this will, I guess, convert the hex into a character, as I showed you a bit before. And then we want to print this one. Okay. I hate using Visual Studio Code's terminal, so I'm going back to the normal terminal and running it. Actually, I may as well do this. So to run it, use Python 3, and then set the file as the argument. Oscar has been XORed. So yeah, we've recovered what the program had done to Oscar and did now have the flag. So what can we do with this now? We have solved the challenge now, but we still have, wait, where did my slides go? Did I close them? Oh, maybe it's like, yeah, okay, no. Aha. So now you can go to our site and I guess go to releases, click on the reverse engineering meetup, click on this first challenge. I forgot to reset this account. And paste the flag in and submit. It says you have already solved this challenge because I submitted the flag earlier, but this would say you have solved it if you have, and it'd say wrong flag if you don't. So yeah, so I think that was a good enough introduction to Ghidra, and we'll be going around and helping you now. Here are the instructions on the hands-on